Hello, this is Weixi. I'm gonna present a joint work done with Kanren and Dan. This is about lambda-Kanren that gives you the power to do higher order logic programming. Lambda-Kanren is inspired by lProlog. Basically, we have implemented the core features of lProlog using the Kanren way. Well, what do we mean by that? First, let's look at lProlog and miniKanren separately. When we are talking about miniKanren, we often refer it to as a programming language that runs backwards. For example, if you write a miniKanren type checker, then you automatically have a type inferencer and type inheritor. And miniKanren relies on the techniques of shallow embedding. The term language is represented by the macros and functions of the host language. Doing so often makes the implementation straightforward and compact. For example, microKanren can be implemented using 40 lines of code, and that is cool. With a compact implementation, miniKanren is easy to be used as a teaching language, and so people can write easy programs and can understand its implementation easily. And often, miniKanren is purely functional. In a miniKanren program, people rarely use class, and to implement miniKanren, people rarely use side effects. On the other hand, lProlog is a theorem prover. It has a more expressive logic than miniKanren that we will go over in this talk, and it has a more powerful unification algorithm. In lProlog, there's a unification algorithm, higher order pattern unification. In higher order pattern unification, you can unify more than structural equivalents. For example, instead of besides unifying quote cat with quote cat, you can unify binding structures such like lambda XX versus lambda YY. So in this talk, I'm gonna first go over the logic that is underlying lProlog and lKanren, and then we will look at the unification algorithm. In miniKanren, we have implemented a first-order Horn clause. This is one way to look at the computational meaning of first-order Horn clause. In miniKanren, you can introduce definitions by using defrel or define, and you can introduce goals by using a run query. lProlog or lKanren implements a more expressive logic called the hereditary Harrop formulas. The difference is that in the Go formulas, there are two actual forms, implication and for all quantification. For a miniKanren programmer, that means in a run query, you can put effectively implication and for all quantification. These two new logic forms correspond to two new operators in lKanren. Implication, we call it assume, and for all quantification is all. All right, now we can see some examples. Here's our first one. Let's define a relation called equal. X is equal to Y if, well, by the first line, if X unifies with Y, that's reflexivity. Or for the second line, transitivity, if there exists some Z such that X is equal to Z and Z is equal to Y, then X equal to Y. And the third line, if Y is equal to X, then we can swap the order and have, if Y is equal to X, then we have X equal to Y. With this definition introduced, we can ask questions or run goals. We can check, well, does there exist some Q so that Q is equal to cat? Yep, so if you ask for one answer, Q is cat. If you ask for more, you will get more cats. You can ask any questions, maybe some silly ones. Apples equal to oranges? Well, obviously no. So when you have an empty list, you can read it as this theorem cannot be proved because we cannot find such a Q to make it true. And with lKanren, you can introduce hypotheses in your running query. For example, you can say, well, assume oranges are dogs. Why do I love dogs? We will have dogs in the future, but why orange? Let's assume if oranges are equal to apples, and then apples equal to oranges. Yeah, then by the symmetric rule, which is the third line in our definition, it is true. Okay. Because every program runs backwards in lambda-Kanren as well, you can put a query or a unification variable in your hypothesis. You can check, well, if we have some q, this q is equal to apples, and then can we make apples equal to oranges? What does this q have to be? Well, it is oranges. Okay, here are dogs. You can nest as many hypotheses as you want. You can say, well, give me 5 things about Q. If I assume apples are oranges and oranges are dogs, then give me 5 things that are equal to oranges. And you have a bunch of them. All right. The effect of assume is only local. Say you run another query immediately after that. Your new query does not have that many crazy hypotheses, and you are getting back to the normal world where oranges are not dogs. Okay, so let's see another example. We can define a relation called PL major, where someone can complete his or her programming language major if this person has taken B521, B522, and 523, these 3 classes. And we can introduce some facts by using def-rel, such as, say we have a guy, Josh, who has taken 521 and 522. Now we can ask questions. For example, can Josh complete his PL major now? Well, he cannot because he's missing a class, 523. So if you run this query, it fails. And we can introduce some hypotheses. For example, assume Josh has taken some class. What this class has to be to complete his major? In this case, is B523, the class Josh is missing. All right, so much for assume. Let's look at the other operator, all. Here's one example. In this case, you can read fresh as fresh or exists. So we can read this as a mathematics theorem. Exists some x, so that for all y, x is y. Well, obviously this is not true, or our system would be inconsistent. So this query fails. We can swap the order. How about this? For all y, there exists some x, so that x is y. That sounds like true, because we can always make that x to be y, and that is provable. This for all operator here, it effectively creates a constant. And this constant is only unifiable with itself or any existential variable that is in the scope. For example, in this case, x is in the scope of y, so they are unifiable. But in the previous one, x is outside of the scope of y, so we cannot unify these 2 variables. All right, here's another example, appendable. We can read this theorem as for all kind of list L, if you append the empty list onto L, then you have L back. If you run this query, lambda-Kanren will prove this theorem automatically for you, giving you an answer that is not empty list. So this theorem is pretty intuitive, but not every intuitive theorem can be automatically or directly proved in lambda-Kanren. Let's say, so we swap the order, let's swap the empty list and L. Here we have another theorem. For all kind of L, appending L on empty list gives you back L. That sounds also true, but Unfortunately, we cannot do that. Well, why is that? Keep in mind, this for all operator, it creates a constant. But if you think about our implementation of appendable, we usually do recursion on the first argument. That means the first argument will be unified either with empty list or at least with a current putter. It seems like a constant cannot be unified with either of them, so unification fails. Or put it another way, this for all operator, it creates a variable that is intentional. We are not making any hypothesis on the structure of this L. To prove this theorem or a kind of workaround theorem, we need to provide some extensional proofs. So instead, we can prove this. Let's say for all A and L, if we assume L, appending L onto empty list is already giving us L. This is like the induction hypothesis. And with this assumption, we can ask lambda-Kanren to prove, well, now I have a larger list counting A on L, and if I'm appending this list onto empty list, can I get back the original list? And that is doable in lambda-Kanren. All right, let's do more examples, more fun examples on proving. Let's just define this very simple relation called proved. And at this moment, only trivial is proved. So you can ask lambda-Kanren, give me everything that is proved. This run star, run for everything. There's only one in the result. That is trivial. Let's try to prove something more interesting than trivial. How about this? For our P, for our Q, P and Q implies Q and P. We can encode for all with the all operator, and we can encode implication with assume. And this conjunction, this and here, it is implicit in the Kanren language. So we can write this. For all P and Q, if we assume P is proved and Q is proved, then we swap the order. We have the Q proved and P proved. You can do this in lambda-Kanren. And maybe another one. Here, for all P, for all Q, if we have P, then we have proved Q or P. All right, how can we encode the disjunction, this OR operator here? Well, it must be conD. So we can ask for all P, for all Q, if we have P proved, then we either have P proved or Q proved. And the lambda-Kanren can prove it for you. Okay, so those are about the two new operators, assume and all. Next, let's look at the unification algorithm and also the extended term language. In lambda-Kanren, you can create binding structures. This TIE here, you can read it as tie or just lambda. So this example shows the unification according to alpha equivalence. So here we are unifying lambda AB, apply A on B, and lambda XY, apply X on Y. They are alpha equivalent by alpha equivalent. All right. This app is effectively an application, and it can recognize beta equivalence as well. For example, let's look at this. Now we are running for some variable f, or say we are synthesizing a variable f, so that lambda A, lambda B, apply A on B is equivalent to lambda X, lambda Y, applying f on X and Y. In this case, what does f have to be to make them equivalent? Well, after beta substitution, we can make the two terms alpha equivalent if f is a function that takes two arguments, and it applies the first argument on the second one, such as this. All right, one last example. Just putting everything together, let's synthesize for some variable f, so that for all x, x is equal to applying f on x. If we ask for one answer, it's obvious that f must be the identity function. If we ask two answers, will we get something else? Maybe lambda underscore 0 x, like a function that takes anything but just gives you x. Well, that is not right in this system, because remember, for all quantified variable can only unify with variable that is in its scope. So in this case, x is not visible to f, so you cannot instantiate f with anything containing x. And this lambda 0, 0 is the only option we have. All right, let's wrap it up. So we have introduced lambda-Kanren. There are 4 new operators in lambda-Kanren. All and assume gives you a more expressive logic, so that in a run query, you can reason about for all quantification and assumption. And lambda-Kanren has a richer language and a more powerful unification algorithms. You can create binding structures using tie and app, and your unifier equal can recognize alpha and beta equivalence between these binding structures. All right, thank you.